Hello again. This is Red Hat Dan on Tech. Today I'm joined by Urvashi Mohnani, who is a principal software engineer at Red Hat. Urvashi actually started work. I hired her as an intern way back a few years ago, not too long ago. And she worked on the Podman team, and now she's working on for OpenShift on the MCO team. So Urvashi, before we start, what does MCO mean?
Hey, Dan, thanks for the great intro. So MCO stands for Machine Config Operator, is one of the portions that make OpenShift work, mainly around the installation and upgrades part. And yeah, you hired me 7 years ago, so it's been a while.
Anyways, so that we're not going to be talking about that today because I don't know anything at the high levels of OpenShift. But we're going to be talking about something else you did while you were still on the Podman team. And it's called Podman Farm or Podman Farm Build specifically. So why don't you tell us about this feature that, I think a lot of people don't know about, but they might be real interested in.
Yep. So Podman Farm was kind of born from the idea of making multi-architecture builds easy and more efficient. So Podman already supported building for multi-architecture platforms by using emulation. So it used the QEMU user static package under the hood to emulate the environment and build. But the thing with emulation is that it can be anywhere from 3 to 5 times slower, just because it's a lot of resources to emulate, and depending on how big of an image you're building, the speed will vary. So obviously, as a user, that would be annoying to you. So we wanted to see if there was a way we could get users to use machines of those native architectures to do the build, but without having to, have those machines physically present with them. So Podman has this concept of system connection, where when you run a Podman socket on another machine, be it a virtual machine or a physical machine that you have, as long as you can connect to that socket, we can send data over there, run the builds on those native architectures, and put them together. So that's kind of the idea of how Podman Farm was built. And we just kind of wanted to use some of the functionality that Podman already has to make multi-architecture builds easier for people and feel like you're just doing it from your own, one machine.
Yeah, it's funny because I've been building, with the Ramalama project we've been playing with, I've been building multi-arch. And I think when most people think of multi-arch, they're talking about x86 and so
Yeah.
people access on a Mac. And then for the rest of the world, it runs on x86. And when I've done it by hand, it's you build it on x86 box, and I go onto my Mac and I build it on a Mac, and I have to push them to a registry, and then I have to create a manifest file, and I have to pull an image from the registry. If I'm on a Mac, I pull the x86 image back to the Mac, I create a manifest list, then I add each one of the images, and then I push that to a registry. So how does Build Farm make that easier?
So Farm Build has basically automated everything that you just described. So when you start off, there's a one-time initial setup where you have to go on those machines to set up the Podman socket and expose that. Once you have that on the local machine where you want to run these builds from, you just have to create a new farm pointing to those sockets. And then when you just have your container file, when you say Podman build, it will send the build context directory and all the build data over to those machines. It will also send any authentication that you need to send over that is on your local machine. The builds will happen on those machines. We will wait for all the builds to happen. Once the builds is done, it will push those builds automatically to a registry. So when you are actually doing a Podman Farm build, you have to give it a fully qualified image name so that we can push it to a registry. Once that is done, we get the digest info back onto the local machine and create a manifest list locally, and then push that manifest list as well to the registry. So everything that you described that you had to do manually is all automated by Podman Farm Build.
And in this talking remotely, that's basically the same thing I do if I'm on a Mac or Windows, because I'm talking into a VM. So instead of, maybe I could, if I'm on my Mac, I could talk to the machine on the Mac, and then I could just set up a x86 in the cloud or something like that. As long as I set up a Podman socket in there, I can actually have my local Podman on a Mac talk to that one and tell it to do a build on my behalf. So that's pretty cool.
Yes.
You got a demo for me?
Yep, I have a demo.
Awesome.
So this is a recorded demo. just because it takes time for multi-arch builds to happen. I want to show the difference between doing it using farm build versus doing it just using Podman build that uses emulation. So we're going to start with the farm build one. So here I have two machines in AWS, two RHEL machines. One is of x86 architecture, one is of ARM architecture here. Let's just hit play. So the first thing I'm doing here is I'm showing that I'm on the x86 and on the ARM architecture. I have just SSH into those machines. And what we're going to do is enable and start the Podman socket using system control. As we can see here, it's active on the, it was active on the ARM one, and now it's doing the same setup on my second VM here. Note that you can do this on any machine, doesn't have to be a virtual machine, and AWS, it can be anywhere that you have access to. Now here I'm back on my local machine, and what I'm going to do is, this is what system connection is in Podman. So here, basically what we do is we set up Podman and tell it that, hey, this is a system connection to this machine, and point it to the Podman socket here. So what I'm going to do here is I'm going to point it to the Podman socket on those two machines that I have, and I'm calling it RHEL AMD and RHEL ARM. So when we do ls, we can see that I have successfully added those two machines to my Podman system connection. And then once you have the Podman system connection set up, you can just do Podman farm create to create a farm. So a farm essentially is a group of system connections. It can be anywhere from 0 to as many as you want. But if your farm has multiple nodes of the same architecture, we just build on the first node that we find for that architecture. So we're not going to like do multiple builds of ARM because we have like 2 or 3 machines in that farm. We just stick to one, and once that is done, we just create the push the image to the registry, and then create the manifest list. So here I've created a new farm called devconf, and I've added the RHEL AMD and RHEL ARM connections there. As you can see, that is set to the default farm. So if I don't specify which farm I want to use when I do Podman farm build, it will automatically default to that. You can have multiple farms as well. You can have different configurations with different types of nodes. That's all up to you. You can customize as you please. Okay, so for this demo, I'm going to build a Llama CPP Python image, which is for an AI model. So it's a pretty big image. So we can see like what the time difference is when we do emulation versus just farm. So here with the Podman farm build command, I'm specifying the farm, pointing into devconf, even though it's default. I just wanted to show that that's the flag that we can use. And one more flag we have here is called local. So by default, local is set to true. What this means is that when you run a farm build, it will build on your farm nodes as well as on your local machine. So if your local machine is of the same architecture as any of the other nodes in the farm, then we won't be building an image for that architecture on the farm node. It will just build locally and push it up to the registry. So same concept, but you can use your local machine as well. But here I don't want to use my local, so I'm setting it to false. I just want to use the 2 nodes in my farm. And as you can see here, I'm giving a fully qualified image name. That's because once the image is built on the farm machines, it's going to directly push it to this registry for me so that I can get the digest from there and then create the manifest list and push. The reason that we did that was we didn't want to spend time moving images around from the farm machines to your local machine to then just push it back to a registry. We wanted to find the most optimal and efficient path. And what we came up with was, let's just directly push it to a registry and then get the digest, build the manifest locally, push that. And when you want to run the image on any of your machines, when you do Podman pull or Podman run, it detects the architecture and pulls the image of that specific architecture for you. So over here, we can see that the build has started. We show which machines we're connecting to. We try to connect there to ensure that we have connection. Once we get like, an okay, we see that those builders are ready, and essentially the farm is ready there. And as you can see, we detect the architecture for those machines. We have the RHEL ARM 64 and AMD 64 architecture, and the image builds just happen in parallel on those 2 machines. And as I mentioned, we wait for all the image builds to happen before we push the image. This is to ensure that we're not pushing the image to a registry and just waiting a while, because when we push the image, we push an untagged image to the registry, and some registries end up clearing untagged images if like there's no name, if there's no tag associated with it, as just like a cleanup mechanism to avoid having any junk around. So we wait for all the builds to happen, push the image there, and then create the manifest list and immediately push that. So this can avoid any of that kind of scenario that may happen. So as we can see here, this build took 3 minutes and 8 seconds with farm build. So the builds happened on an ARM64 and AMD 64 machine. Those were those native architectures. So we were not using any emulation anywhere, no emulation anywhere. And when we inspect the manifest list that we have locally, we see we have both the ARM64 and AMD 64 architecture in there. So that was farm build. And when we go to Quay, oops, let me just go back a bit. That was pretty quick. So when we go to Quay, we can see those different architectures here for the image. As you saw, I called it Llama Farm. And you can see that it has the ARM64 and AMD 64 child manifest associated with it.
Yeah. So I could use this if I had a Podman sitting on a Power PC or any other architecture, that we has Podman on it, then we should be able to do the same thing, right?
Yes, any architecture is supported. I just use ARM and AMD because those are the most popular ones right now.
Okay. Yeah, that's
Yeah.
awesome.
Yep. All right, so that was farm. So now let's take a look at, sorry, we can skip this. All right. So that was farm. So now let's take a look at, when we build just using Podman build that uses emulation. So the first thing that I need to do is I need to create a manifest locally. As Dan mentioned, you have to do that manually. So that's what the Podman manifest create command. But that manifest will be empty right now because we haven't added any images to it. And then what I need to do next is with the Podman build command, I need to specify the architectures that I want to build for using the platform flag. And then I have to pass in the manifest that I want to add these images to, and then just point it to my container file as normal. And here we can see that the build has started. So we're going to time this one as well. So this build happens locally on your machine. It uses QEMU, uses static to emulate those different architecture environments for you. I'm skipping a bunch ahead here in the recording just because it takes a bit. So let's just kind of skip ahead.
And you're doing it sequentially, not in parallel.
Yes, this will happen sequentially. Yes, that's correct. So as we can see here, this build finished and it basically took 11 minutes and 35 seconds. So that's like almost 4 times more of what we saw with Podman farm build.
Yeah, it's funny because we've talked. I've been talking about with RHEL GCC developers, and they hate emulation. They just don't think it's unsupported. They think it's unsupported, so they really recommend against doing emulation builds. And matter of fact, the code is not even available, I believe, in RHEL at all. So this really makes it easier. I've talked a lot in the Rivos world where a lot of their architecture is based on ARM, and then but the test systems are all in x86.
Yeah.
So they can build the same application both for ARM and x86, but they can run through, use CI/CD systems using x86 machines to test it, and then they might have very few sort of test machines for the new hardware they're going to be building for edge devices. So this makes it pretty easy. The initial setup is a little painful because you have to set up a separate node with a socket. But once you have that up and running, then you should be able to do this all day long. And you can plug it into CI/CD systems. You don't need to do this obviously locally on a laptop, but it's really, really cool. So it's Podman Farm. Do you any plans for any other farms, or just for farm builds at this point?
I think at this point, just for farm builds.
Yeah.
Yes.
Okay. No, that's really, really cool.
Yeah. One thing I kind of want to mention quickly, I'll quickly show. So I put this diagram together so it's kind of easy to understand what is going on. I already went through this in the beginning of the talk and kind of throughout the demo, but just it's nicer when you can visualize it. So basically, you have your local machine. This is where you set up those system connections pointing to your farm nodes. You can have, as I said, as many farm clusters as you would like. And then you just have to set up the Podman socket on each of these nodes that will be in your farm. Once that's set up, when you do a Podman farm build, we send the build data over to these farm nodes. They do the builds and they push the image directly to the registry. Once that's done, we get the digest back onto the local machine, create the manifest on the local machine, and then push the manifest list to the registry. So that's essentially the whole workflow of what Podman Farm Build is doing.
Okay. Yeah, I wanted to follow up on that. The mecha you talked earlier about you push the images and they're untagged. Because one of the things I worry about when I push to a registry, say I'm doing an update of an existing package on the registry, and I want to replace the latest version. We don't replace you push both images get pushed to the registry as untagged, and then you assemble the manifest, and then you push the manifest. And it's only when that manifest gets pushed to the registry that the latest tag gets replaced. So it's really that's going to either be successful or not. So you don't have a chance of like having a newer version of x86 and an older version of ARM on underneath the tag. It's only when the manifest tag gets replaced. So,
yes,
so
right.
that's excellent.
Yes.
And this is great. So this is available in Podman 5 everywhere.
Yes.
Yeah.
Yes, that's
Podman 5. And Podman 5 is just about to be shipped on. Was it available on 4?
It was available from 4.9 onwards.
Well, all right. So it's available on our RHEL now. I was just because RHEL doesn't have Podman 5 yet, but it's about to be released. All right. Well, it's great seeing you and great talking to you. And everybody go and try out Podman Farms.
Thank you for having me, Dan.